A woman stood in the factory, directing her flashlight beam into a narrow aluminum tube. What she discovered inside troubled her deeply. The metal surface bore unusual marks, not the random scratches of careless handling, but parallel grooves running the length of the tube with disturbing uniformity. She marked it with chalk and set it aside. This was the 5th defective piece in just 1 hour. The location was the Willow Run facility, situated 35 miles from Detroit. The time was November of 1942. This woman was among many inspectors, working day shifts, scrutinizing countless metal tubes destined for bomber fuel lines, hydraulic systems, and dry-sing equipment. These tubes would become vital components of B-24 Liberator aircraft. Training had prepared inspectors to identify various problems: fractures in the metal, poor welding, incorrect measurements, and foreign contamination. However, they began noticing something unexpected. Brand new parts, fresh from manufacturing equipment, showed damage to the aluminum itself. Scratches appeared, gouges marred surfaces. Deformations existed where none should be. Inspectors documented their discoveries. Management reviewed the rejected components. Technical specialists arrived to investigate. Their findings would reveal a critical miscalculation, threatening America's entire heavy bomber manufacturing program. The issue wasn't deliberate sabotage. It wasn't incompetent workers. The problem ran deeper and proved more concerning. Ford Motor Company, representing the pinnacle of global manufacturing capability, had attempted to apply its celebrated automotive techniques to aircraft construction. They failed to recognize that aluminum and steel demanded fundamentally different treatment. The hardened steel tools that shaped car components with remarkable efficiency were destroying the soft aluminum pieces comprising 85% of the B-24 Liberator structure. When the full scale of this problem became apparent, Ford had completed 56 bombers during 1942. Military inspectors rejected every single aircraft for combat duty. These planes would serve at training facilities. They could fly reconnaissance over secure areas. They might transport cargo. But they would never drop bombs on enemy targets. They wouldn't face hostile aircraft or anti-aircraft weaponry. The military determined they simply weren't reliable enough for combat operations. The dies and machinery representing millions in investment required complete replacement and redesign. Critics who had questioned Ford's ability to mass-produce heavy bombers felt vindicated. Journalists began mockingly referring to the facility as Will It Run instead of Willow Run. Senator Harry Truman, leading a committee investigating wartime production inefficiencies, visited the plant with obvious skepticism. The arsenal of democracy, America's ambitious commitment to defeat Axis powers through industrial supremacy, was producing bombers incapable of fighting. This story begins not with failure, but with extraordinary confidence. During 1941, Ford Motor Company stood as the most accomplished manufacturing organization in human history. Henry Ford had transformed industrial production through the moving assembly line concept. His River Rouge complex in Dearborn stretched across 2,000 acres and represented a marvel of vertical integration. Raw materials entered at one end. Completed automobiles emerged from the other. Ford owned iron ore mines and transported materials on Ford-owned ships. Ford coal mines provided fuel. Ford rubber plantations supplied tires. The company smelted steel, generated electricity, manufactured glass, and produced virtually every component going into Ford vehicles. Production efficiency was legendary. In 1936, Ford could transform raw iron ore into a finished automobile in 41 hours. The Model T, which once required 12 hours to assemble, rolled off production lines every 93 minutes by 1913. By the 1920s, Highland Park facilities could complete a Model T in 93 minutes. With individual plants producing over 1 million vehicles annually, Ford's mastery of mass production had made automobiles affordable for ordinary Americans. and elevated the United States to leadership in global industrial power. This confidence in mass production wasn't baseless. Ford techniques had been studied, replicated, and adapted by manufacturers worldwide. The Soviet Union's massive Gorky plant was modeled directly on River Rouge. Nazi Germany's Volkswagen facility employed Ford-inspired methods. When the United States entered World War II, government planners naturally looked toward America's automotive industry to produce the enormous quantities of military equipment needed for global warfare. Aircraft, tanks, artillery, trucks, jeepster. American military would require them all for unprecedented volumes. If anyone could produce them, it was automotive manufacturers who had perfected mass production through decades of experience. The challenge arrived on May 26, 1940, when President Franklin Roosevelt delivered a radio address that shocked millions of listeners. Roosevelt announced a goal to gear the nation toward producing at least 50,000 airplanes yearly. 50,000 combat aircraft within 12 months. This target exceeded the total number of planes built in the United States since the Wright brothers' first flight at Kitty Hawk in 1903. At the time, the country possessed fewer than 3,000 military aircraft, most obsolete. The aviation industry, accustomed to handcrafting planes in relatively small quantities, was completely unprepared for this scale of production. Roosevelt and his advisors believed long-range, high-altitude heavy bombers would become the decisive weapon in coming warfare. The B-17 Flying Fortress developed by Boeing had proven itself in early European combat operations. Even more capable was the consolidated B-4 Liberator, a twin-finned, high-winged heavy bomber with dual bomb bays and impressive operational range. The B-24 could fly farther, carry more bombs, and operate at higher altitudes than most contemporary aircraft. It was also more complex than any plane previously designed for mass production. At 67 feet long, the B-24 contained 450,000 individual parts and 360,000 rivets in 550 different sizes. A single B-24 weighed 18 tons. By comparison, a typical automobile of that era contained 15,000 parts and weighed approximately 3,000 pounds. Consolidated Aircraft in San Diego had designed the B-24, but the company lacked facilities and production capacity to build bombers in quantities the military required. Consolidated Methods represented traditional aircraft manufacturing skilled craftsmen, building planes largely by hand. Each aircraft was essentially custom-made using jigs and temporary fixtures. This approach excelled at producing high-quality aircraft in modest numbers, but proved completely inadequate for the scale Roosevelt demanded. The government needed someone who could apply industrial mass production techniques to heavy bomber manufacturing. They needed Ford. Charles Sorensen, Henry Ford's right-hand man and production chief, visited Consolidated's San Diego facility in January 1941 to assess operations. What he observed shocked him. Workers were building aluminum airplanes outdoors on steel fixtures. Components were handcrafted to fit individual aircraft. There were no interchangeable parts, no standardized assemblies, no moving assembly lines. Everything Sorensen understood about efficient production was absent. They were building airplanes the way Ford had built cars in 1908, but Sorensen recognized opportunity. If Ford could apply automotive production methods to aircraft manufacturing, the company could revolutionize bomber production. Sorensen believed Ford could build B-24s on moving assembly lines with standardized interchangeable components. He proposed building not just some B-24 components, but complete aircraft hundreds monthly, rolling off lines with the same efficiency that produced Ford automobiles. The Army Air Forces, desperate for bombers, eagerly accepted this proposal. In February 1941, contracts were signed. Ford would construct a massive new plant dedicated to B-24 production. Sorensen made a bold promise. Willow Run would produce one B-24 bomber every hour, 60 aircraft daily, 1,800 monthly. The claim seemed impossibly ambitious, even by Ford's standards. Aviation industry leaders were openly skeptical. Dutch Kindleberger, president of North American Aviation, scoffed that you couldn't expect a blacksmith to make a watch overnight. Others pointed out that aircraft required precision and quality control far beyond automotive manufacturing. A car with minor defects might break down on roads. An aircraft with identical defects could kill its crew and fail its mission. Tolerances were tighter, consequences of failure more severe, and complexity vastly greater than anything automotive manufacturers had attempted. Ford pressed ahead with characteristic confidence. The company selected a site on farmland personally owned by Henry Ford near Ypsilanti Village, 35 miles west of Detroit. Architect Albert Kahn, who had designed River Rouge, was commissioned to create what he boasted would be the most enormous room in human history. The specifications were staggering: 3.5 million square feet of factory space under a single roof, an aircraft assembly line over a mile long with a massive turntable that could rotate partially assembled B-24s 90 degrees to move them through different production stages, 6 runways and 3 aircraft hangars on adjacent property where completed bombers would be tested and prepared for delivery. At peak capacity, the plant would employ over 100,000 workers. Construction began in April 1941. Concrete was poured continuously, day and night. Steel frameworks rose across flat farmland. Within months, the massive structure took shape. It was, as promised, the largest factory building in the world, stretching so far that workers at one end could barely see the other. Ford equipped Willow Run with the latest production machinery, much designed specifically for this project. Die-making facilities could produce steel dies needed to stamp metal components into shape. Machine shops could manufacture fixtures, jigs, and tools required for precision assembly. Testing equipment would verify that every component met specifications. The plant had its own power generation, water supply, and fire department. It was essentially a complete city dedicated to one purpose: building B-24 Liberators. The plant's official dedication ceremony on October 22, 1941, drew Major Jimmy Doolittle of the United States Army Air Forces, who would later become famous for leading the first bombing raid on Tokyo. Doolittle praised Ford's commitment and expressed confidence that Willow Run would make decisive contributions to America's military preparedness. Henry Ford himself, although officially retired, attended the ceremony. At 78 years old, Ford represented American industrial achievement. He had transformed manufacturing, created the middle class through high wages, and proven that American ingenuity could solve any production challenge. If Ford declared Willow Run would produce a bomber hourly, skeptics hesitated to bet against him. Production officially began during summer 1941. Workers, many hired from Detroit's automotive plants, arrived for training on aircraft assembly. Differences from automotive work quickly became apparent. Aircraft components required precision yeared in thousandths of an inch. Assembly procedures were more complex, with multiple steps performed in exact sequence. Unlike cars, where a single worker might install identical components on vehicle after vehicle, aircraft assembly required teams working together on large sub-assemblies that were then integrated into final aircraft. Ford's managers remained confident. They had scaled up automotive production before. They had thousands of workers trained on complex assembly procedures. They had solved countless production challenges through engineering and process improvement. Aircraft manufacturing might be more complex than automotive production, but fundamental principles remained the same. Break work into simple, repeatable steps, standardize components, create efficient material flow, minimize wasted motion, and drive toward continuous improvement. The Ford production system, refined over decades, would triumph over traditional inefficient methods used by aircraft manufacturers. Tooling was key. Ford invested heavily in dies, fixtures, and machinery specifically designed for B-24 production. For automotive manufacturing, Ford used hardened steel dies that could stamp sheet metal parts with tremendous force, creating precise shapes quickly and reliably. These dies lasted 4 millions of cycles and produced parts with consistent dimensions. Ford's engineers reasoned the same approach would work for aircraft components. They specified hard steel dies for stamping aluminum parts that would comprise B-24 structure, skin, and internal components. This decision seemed entirely logical. Steel was stronger than aluminum. Hard steel dies had proven themselves in automotive production. Ford's die-making capabilities were second to none. The company's die shops could produce complex multi-stage dies that formed intricate shapes with minimal waste. These dies were engineering marvels representing decades of accumulated knowledge about metal forming, tool steel, metallurgy, and production efficiency. Using these proven dies for aircraft production seemed not just reasonable but obvious. No one at Ford during those early months seriously questioned this approach. The company's engineers had designed automobiles for decades. They understood metal forming, stamping, and fabrication better than almost anyone in the world. Aircraft manufacturers might handcraft their components with softer dies and more manual labor, but Ford would bring modern mass production methods to the industry. Hard steel dies would stamp out B-24 components with the same efficiency that produced car parts. If aircraft manufacturers warned this wouldn't work, they were simply protecting outdated methods against Ford's superior technology. The first components came off Willow Run production lines in November 1941. Initially, Ford was only contracted to produce B-24 parts that would be shipped to Consolidated in San Diego or Douglas Aircraft in Oklahoma for final assembly. By October 1941, Ford had negotiated permission to assemble complete B-24s at Willow Run. This required even more sophisticated tooling and assembly procedures. Ford's engineers designed assembly fixtures for the B-24s, major sub-assemblies, wings, fuselage, tail section, and bomb bay. Each fixture had to hold components precisely in position, while workers installed fasteners, sealed joints, and integrated systems. The dies went into service. Sheet aluminum moved through stamping presses. Components began accumulating in inventory. Assembly work proceeded. Workers learned their tasks. Supervisors managed production flow. The massive assembly line began operating, moving partially completed structures through station after station. From the outside, Willow Run appeared to be fulfilling its promise. The largest aircraft factory in the world was producing B-24 components on unprecedented scale. The arsenal of democracy was becoming reality, but quality inspectors, including the young woman with the flashlight examining tubing for defects, were beginning to find problems. Small at first, a few scratched components here and there, some dimensional variations, minor deformations that might be within acceptable tolerances but seemed more common than expected. Inspectors performed their jobs, marking defective parts for rework or rejection. As production ramped up through late 1941 and into early 1942, the defect rate didn't decrease. If anything, it increased. More scratched aluminum, more gouged surfaces, more components that didn't quite meet specifications. Then came the first assembled aircraft. The first B-24 Liberator, built entirely at Willow Run, rolled off the assembly line in September 1942, nearly a year behind schedule. It should have been a triumph. Instead, it became the beginning of a reckoning. When Army Air Forces inspectors examined that first bomber and the 55 that followed during the final months of 1942, they found what quality inspectors at Willow Run had been reporting for months. The aluminum was damaged, not catastrophically, not obviously visible to casual inspection, but present throughout the aircraft in ways that compromised structural integrity, created stress concentrations, and reduced safety margins that meant the difference between an aircraft that could withstand combat damage and one that would fail under stress. The Army rejected every single one of the 56 B-24s Ford produced in 1942 for combat operations. They were assigned instead to training bases where students could learn on them without combat risk. They could fly reconnaissance missions over safe territory. They could serve as transports, but they wouldn't carry bombs over Germany or Japan. They would not face enemy fighters or anti-aircraft fire because the Army Air Forces had determined they simply weren't safe enough for combat. Charles Sorensen had promised 1 bomber per hour. Ford had delivered 56 unfit bombers in an entire year. The critics had been right. The blacksmith couldn't make a watch overnight. Somewhere in the massive expanse of Willow Run, amid 3.5 million square feet of production space and the mile-long assembly line, a young woman with a flashlight continued examining tubing, marking defects with chalk, and watching as the components she rejected piled higher each day. The problem was metallurgical. Although it took weeks for Ford's engineers to fully understand it, aluminum and steel are fundamentally different materials with different properties, and those differences matter profoundly when farming metal under pressure. Steel, particularly tall steel used in automotive dies, has a Rockwell hardness of approximately 58 to 62 on the C scale. It can withstand tremendous compressive forces without deforming. When a steel die stamped sheet steel in automotive production, both materials were hard enough that the die created clean forming action. The die didn't scratch or gouge the steel sheet because both materials had similar hardness characteristics. Stamped parts emerged with clean surfaces, precise dimensions, and no damage to metal structure. Aluminum alloy 2020-43, the primary structural material in the B-4 Liberator, has a Rockwell hardness of approximately 60 to 70 on the B scale, which converts to approximately 10 to 15 on the C scale. The difference isn't subtle. Aluminum is dramatically softer than tall steel. When a hard steel die stamps aluminum sheet under the same pressures used for steel automotive parts, the die doesn't just form the aluminum, it scores it, scratches it, and creates microscopic tears in the metal surface. Ford's engineers had designed dies based on automotive production parameters. Stamping pressures were calibrated for steel. Die surfaces, while polished, were hard enough to cut into soft aluminum harder than merely shaping it. Forming speed, optimized for steel's properties, was too aggressive for aluminum's different characteristics. Every time a die struck aluminum sheet, it caused some damage. Multiply that by thousands of parts daily, and the defect rate climbed rapidly. The scratches and gouges weren't merely cosmetic. In aircraft structures subject to tremendous stress, surface damage creates stress concentration points where cracks can initiate. Aircraft undergo constant vibration, temperature cycling, and loading that far exceeds anything experienced by an automobile. The airframe must withstand these stresses for hundreds of flight hours. Surface damage that would be inconsequential in a car fender becomes critical in an aircraft wing spar or fuselage frame. The scratches reduced the metal's fatigue life, compromised structural integrity, and created potential failure points. Metallurgical laboratories at Willow Run examined damaged components under microscopes. They could see scoring patterns clearly. Scratches ran in consistent directions, matching die movement during stamping. Some gouges penetrated deep enough to remove measurable material. Metal surrounding damage showed signs of work hardening, where dies had compressed it excessively. In the most severe cases, aluminum showed evidence of galling, where harder steel had actually torn microscopic particles from the softer aluminum surface. Quality control protocols required inspectors to examine components at multiple production stages. For critical structural elements, every part received visual inspection under adequate lighting. Tubing received internal inspection using small flashlights or specialized optical equipment to detect interior defects. Major assemblies were checked for dimensional accuracy using precision measurement tools. Acceptance criteria were strict because aircraft safety demanded it. Unlike automotive production, where a certain defect rate could be tolerated and corrected through warranty repairs, aircraft defects could prove catastrophic. Inspection records told a troubling story. In November 1941, as production ramped up, inspectors rejected approximately 8% of stamped aluminum components for surface damage. By December, the rejection rate had climbed to 12%. In January 1942, it reached 15%. Rejected parts had to be either reworked, if possible, or scrapped entirely. Rework was labor-intensive and didn't always restore components to full specification. Scrapping meant wasted material, wasted labor, and production delays while replacement parts were manufactured. Production supervisors pressured inspectors to accept marginal components. The plant was under enormous pressure to meet delivery targets. Every rejected part delayed bomber completion, but Army Air Forces inspectors maintained their standards. They understood that scratched aluminum wasn't acceptable in combat aircraft. They had seen what happened when structural components failed under stress. Aircraft broke apart in flight. Crews died. Standards existed for good reasons, and the Army wouldn't compromise them regardless of production pressures. Charles Sorensen reviewed defect reports with growing concern. Rejection rates weren't decreasing as workers gained experience. They were increasing. That suggested the problem wasn't worker error or insufficient training. It was systemic. Something fundamental in the production process was causing consistent damage to aluminum components. Sorensen ordered a comprehensive investigation. Teams of engineers examined every stage of the stamping process. They measured die clearances, stamping pressures, forming speeds, and material properties. They tested different lubricants to see if better lubrication could protect aluminum. They tried reducing stamping pressures, although that risked incomplete forming. They experimented with die surface treatments to make steel less abrasive. Nothing worked consistently. Hard steel dies kept damaging soft aluminum. The breakthrough came when engineers compared Ford's dies to those used by Consolidated Aircraft in San Diego. Consolidated used dies made from softer materials, including Kirksiter zinc aluminum alloy with much lower hardness than tool steel. These softer dies wore out faster than steel dies, requiring more frequent replacement. They couldn't handle the high production volumes Ford planned, but they didn't damage aluminum. The softer die material formed aluminum without scoring or gouging it. Surface finish on Consolidated stamped parts was clean, without scratches plaguing Willow Run's production. The implications were devastating. Ford's entire tooling strategy for the B-24 was based on hard steel dies designed for automotive production. The company had invested millions of dollars in design, manufacturing, and installation. Thousands of dies were in production or in inventory ready for use. Die shops were manufacturing more constantly to support anticipated production increases. The dies represented one of Ford's largest investments in the Willow Run project, second only to the building itself. And they were fundamentally wrong for aircraft production. Changing to softer dies meant more than just buying different material. It meant completely redesigning the stamping process. Softer dies required different press settings, different forming sequences, different maintenance schedules. The dies would wear out faster, requiring frequent replacement. Ford would need to manufacture replacement dies continuously, increasing cost and complexity. The production schedule, already behind target, would face further delays while new dies were designed, manufactured, tested, and installed. The hard steel dies that had seemed like Ford's competitive advantage, the application of proven automotive technology to aircraft manufacturing, had become the project's greatest liability. By September 1942, Willow Run had assembled its first complete B-24 Liberator. It rolled off the mile-long assembly line amid ceremony and celebration, photographed for newspapers across the country. Here was proof that American industry could rise to any challenge. Ford Motor Company, applying its legendary production methods to aircraft manufacturing, had built a heavy bomber. The arsenal of democracy was real. Army Air Forces inspectors arrived to examine the aircraft for acceptance. They came with clipboards, measurement tools, and detailed checklists covering hundreds of inspection points. They examined airframe structure, control surfaces, hydraulic systems, electrical installations, and fuel lines. They checked dimensions, tested systems, and documented every finding. Their inspection took days, working through the aircraft methodically, section by section. The inspection reports were damning: scratched aluminum throughout the airframe, gouged tubing in the fuel system, surface damage on structural components, dimensional variations exceeding acceptable tolerances, incomplete forming on stamp parts where dies hadn't applied sufficient pressure, poor fit between components that should have been interchangeable. The aircraft met some specifications, but failed others critically. Most troubling were structural issues. Wing spars showed surface damage. Fuselage frames had scratches in high-stress areas. The problems weren't obvious to casual observation, but they were real and serious. The Army rejected the aircraft for combat operations. It could serve as a trainer, operating under less demanding conditions with reduced stress on the airframe, but it wouldn't face enemy fire, wouldn't fly long-range missions over hostile territory, wouldn't carry the bombs and crews that depended on every component functioning flawlessly under extreme conditions. For an aircraft designed as a heavy bomber, being relegated to training status was failure. The second B-24 off the line faced the same inspection, the same rejection, then the third, the fourth. By the time 56 aircraft had been assembled and inspected in 1942, the pattern was undeniable. Every single bomber failed to meet combat standards. Some had more defects than others, but none were acceptable for the mission they were designed to perform. The Army assigned all 56 to training bases, reconnaissance duties, and transport operations. Combat units in Europe and the Pacific would receive B-24s from other manufacturers, not from Willow Run. The financial costs were staggering. Each B-24 required approximately 150,000 man-hours to build using materials worth tens of thousands of dollars. Ford had invested those resources into 56 aircraft that couldn't fulfill their intended purpose. The dies represented an additional investment of millions of dollars. The dies couldn't be salvaged or repurposed. Hard steel dies designed for automotive production had no place in aircraft manufacturing. They would have to be scrapped, all of them. Thousands of dies representing months of engineering work and manufacturing effort were worthless for B-24 production. New dies would have to be designed from scratch using softer materials suitable for aluminum. Die shops would have to retool entirely. Stamping presses would require recalibration. Assembly fixtures might need modification. If new dies produce parts with slightly different dimensions, the production schedule, already a year behind Charles Sorensen's optimistic projections, would face further delays measured in months. Press coverage turned savage. Newspapers that had celebrated Willow Run's construction now mocked its failures. Will It Run became a standard joke. Editorial cartoons depicted the massive factory, producing nothing but delays and excuses. Critics who had warned that automobile manufacturers couldn't build aircraft claimed vindication. Aviation industry executives who had resented Ford's confident entry into their field privately enjoyed the company's embarrassment while publicly expressing sympathy.